simulations or DNA break simulations if you are doing nano dosimetric simulations. So it's like I said before, you should go to the Gen4 website, look for latest publication, and look for like which physics list covers the range
Okay.
that you are interested in, and this way it is easier for you if you want to design some like a Gen for modular physics list with by combining several other reference physics lists which are pre-made or pre-added for you. So these actually this one G G4EM standard op 3 is actually the Gen 4 physics list that they have given a new name in Topaz in this format, but actually they are what they and the Gen 4 has published in their paper too. So it's just the same thing. Only thing is to while developing a develop wrapper around Gen 4, they came up ended up with these kind of names. So here they have used option 0, and you'll see that the energy range no, they have not provided energy range here, but they have provided like which gen, for example, contains these information. And but yeah, sure, this paper actually quotes all the range of energy range in which uh, this physics-less work, or they cover the particle simulations. Yep. So they have shown four types. Three are like modular, and another one is the reference type. So you see here they do not use Gent for modular. They specify Q QGSP, but high energy physics. So it's actually high energy physics physics list, and yeah, that's it. So you can set your physics list in this format, and if you see the exam, now is the time that we go visit our uh, file that I have created for this project or this workshop. Okay, so you see this initially it's a graphical user interface definition, and then it's the see there's basically the Topaz uh, software parameter that you have to define, and that number of threads means how much uh, threads of your computer or cores of your computer that you want to use in the simulation. So if you add to 0, the Topaz will automatically decide. You don't have to do anything about it. Here I have defined, we don't need this. So I've defined the tumor material as material. This is how you need to define your material. So basically, we already discussed answers, so you can check, revisit the video I have already uploaded on YouTube on material definition. Then it's the world, like I said, we have to define, take care of. If we want to handle our world volume definition ourselves, we should do it. This way, it gives us more freedom and control over our simulation. Then this base, it has like a, let me run first uh, because it uses it. So mhm. So first, yeah. Okay. Okay, so you see, like I mentioned before in earlier videos, we have like three boxes. First one is the shielding box. This upper box is a shielding box made up of lead or any polymer like PEEK. And then this box that contains iodine 125 seed at its center is filled with air. Then this is a water phantom, or you can call it a box box composed of tumor material. And these yellow grids are our voxels that I have assigned to score dose and photon fluence. So now let's check the input file. So I already showed you the material definition here, the world volume. So this outer white box that contains all the components of our simulation is our world volume. It should be larger than our normal volumes, whatever we are using, and it should include everything that we are simulating. And why it's like generally we keep it a little bit bigger. Why it's this much larger? It's because of our source size. The particles that will be going out of this dimensions are what is the in x-axis direction will are not important for me in more than this boundary. So that's why I restricted my world in this way. Okay, so yep. So we have a shielding base, which is made up of PEEK here. PEEK is a kind of a polymer, so it's nothing important. You can keep it lead, so it's not a problem. Then is the box where I have placed the source. It is made up of air, like I said. Then we have another box, tumor. It is made up of tumor material, and I have given different colors and given it a different color in the form of grass, and all of them are fully wireframe. So like I showed you earlier, you can use cloud so to show them, and, or like solid to show if they're it's just a visualization type where you can choose whatever suits your example or your simulation, and which one you are comfortable with. So you see. Okay. Now is the physics setting. So I have used the one module of so I have used the Gnt for modular, and I have customized it. So I have used the Gnt for EM Livermore physics list because it covers this energy range of for iodine 125 mean energy is around 30 kV. So we want a physics list that can include that can simulate particles in this energy range. So if you go back to this, so here is probably Livermore, yeah, EM Livermore physics list, and here you can find the energy range also. Oh, it's going down. Yeah, here. So if you Livermore ionization model, so it goes from like 1 MeV to zero point 0.1 keV. So this suits best for our simulation. And then there is a cutoff for electron and gamma. Let's check about this. What is it? Because we already checked about the, yeah. So here you can assign r- cuts. First is cut. Yeah, cut affects the entire world, but do they have more information here? No, so they just talk about like physics list, available modules. You can check directly on the Gen 4 website also. No, no. Mhm. Yeah, so these are the modules available, and these are the names that are given in Gen 4, like I said, and in Topaz they have little bit different name in they are not caps lock used. And remaining option of the physics. Okay, you can define physics regions by defining, allowing, putting a cut to them, like what range of particle, like if you have a photon that has a range of around like 10 centimeters, and you are not interested in any particle that has that has a range of like zero point 0.1 so you can add it as a cut. Like here they have added a cut for gamma as 0.05, and like in our case we have voxel size of zero point 0.3 millimeter. So okay, first go through, let me show you first the voxel. This is actually our source. You see the source definition, it is a volumetric source, and here I have defined the geometry of our source. So you can check this, you already have a file of it. And the example of this iodine 125 sources present in the brachytherapy directory as well. Yeah, here is the our voxel. So you see this I have defined as a scorer, and I have scored the dose in the form of a grid, and it is going to be parallel. So is parallel is true. Here are the like if I have chosen a box, so it has x, y, and z half length. So actual dimension is 6 mm by 6 mm by 6 mm, and each of them is divided into 20 voxels. So 6 by 20 gives you like 0.3 millimeter. Yeah, 0.3 millimeter. So the dimension of the voxel we have is point 0.3, point 0.3, point 0.3. So this way you can decide your cut for your physics. Like zero point 0.5 mm is too big, so we are not interested in anything that is bigger than uh, f- zero point 0.5 mm for our smaller than zero point 0.5 mm uh, for our simulation. And similarly for gamma, we are not interested in more than one, if it is less than 1 centimeter. So I have tuned these parameter for my simulation, and I'm simulating like Auger electrons, Auger cascade, the fluorescence, de-excitation, ignore cut, and peaks. So you can turn on. They are not generally not on automatically, but sometimes that when we are working at low energy, we are interested in these particle simulations, so you have to make them true when you are doing such simulations. Okay, and yeah, so this covers our physics. Reference physics list. Like I said, this is a type of reference physics list that is already made for you, so you have to you can just directly import it into your simulation. And here is other list of uh, no, they say that okay, here are the reference physics list they have provided. So yeah, here you can check which means which physics list is for what purpose, and you can take that information and check if fits with your requirements or not. Okay, optical physics is for optical photons. I have never used it, and we will not use here for this workshop. So for now, I'm skipping it. But yeah, definitely you can relook into it, and if you are interested in simulating optical photons. Yeah, here generally it's like how you can tune your physics list and make use of multiple physics lists. That's it. And you can set a threshold on the emitted particle type, the step size, the maximum range that you want to simulate, or you want your particle to take the steps, so you can provide set that too. Yep. That's it. So we have covered physics and the particle source type. So if you have any questions, let me know. I will answer them. I try to keep it simple by switching between the examples and the theory so that you don't get confused. Like instead, sometimes we keep on reading theory and we don't see the input file. It is little bit, and the things get like
Confusing. Yeah.
yeah, so I wanted to keep an interaction by running simulations, showing it the input file and showing the documentations because you will be in the same environment when you'll be designing your input file. So you need to know how to switch and what to copy, paste, or how to write your thing into your input file. Yeah, so
Yeah.
feel free to ask your questions if you have any.
Yeah. I think when I practice and I encounter any problem, then I can ask a question from there.
Okay, so you don't have any questions for now?
Yes.
Okay, perfect. So tomorrow we can discuss on this scorer. We'll discuss about the scoring the dose,
Okay.
and we'll get a output. Yep. So tomorrow our aim is to read the different type of scorers and different facilities available in Topaz for this. And yeah. And I will talk about one other perspective, that is track length estimator. So it is a specific uh, dosimetry scoring technique that is developed particularly for brachytherapy applications. So you can check its documentation here also in Topaz. They have this track length estimator. Yeah. And so it's in the brachytherapy package, and
Okay.
you can check like it. It actually speeds up your simulation, and there I am not uh, considering or describing the complete physics of it, but yeah, sure, you can look into this particular paper they where they have defined the strike length estimator. Uh, it's yeah. Where is that paper? Yeah, it's here. Algebra. Algebra was a code developed here in by a research group from Laval University here in Canada, where I'm working currently now, and they developed this track length estimator technique for calculating absorb dose and brachytherapy simulations to speed up. Actually, it uses um, like it is a you can consider it as um what is the I forget the name. It's like a
Reference.
variance reduction technique to speed up the simulation. So
Okay.
we'll cover this tomorrow because I have used it in scoring the dose. So I have used the track length estimator. So tomorrow our focus will be to calculate the dose and the fluence. So okay then. See you tomorrow.
Okay. All